I'm Mike Halley. I'm a scientist here at the IIC, and for half my time, and the other half of my time, I'm at the surgical planning lab at Brigham and Women's Hospital, from whence my boss, who is the speaker, Ron Kakinis, hails from. And Ron and I have actually worked together since about the time when he came to the US around 1988. He founded the surgical planning lab here in 1990. He received his MD from the University of Zurich in Switzerland in 1982. And in between then, he was at the ETH in Zurich, where he took the medical side of things, combined it with image processing, and really formed the basis of what the surgical planning lab has done since then under his direction, which is bring imaging and medicine together in ways that really help people and advance research. And so it's my distinct pleasure to welcome him to give a talk here. And so please welcome Ron.
So it's quite a pleasure to be here, and I hope you like the presentation that I'll give you. I took the habit a few years ago to start with the acknowledgements instead of putting them at the end, because most of the work that I'm presenting was not done by me, obviously, but done by people that work with me. And I think it's very important to acknowledge that fact. And as you see, there are also as many logos as you might find on some race cars, which are all the funding agencies and entities that are also contributing and making this effort possible. So the names that you see here are more senior people, more the principals, but on many of my slides you'll find pictures with names acknowledged, and those are the people that actually did the work. I would say 95% of the slides, the pictures on slides that you'll see represent each of them a peer-reviewed journal paper. So it's not just pretty pictures, but each of them there is depth behind it. So my presentation is basically structured like this. I'll talk a little bit philosophy, then about the lab, Surgical Planning Laboratory, SPL. I'll give two examples of some of the science that we are doing. Initially I had more examples, but then I decided to cut it down to a few examples so that I could spend a little bit more time per example. I'll also talk, so there is some science there, there's also some engineering there. And the two are distinct but have to go hand in hand in many of our endeavors. And then finally I'll talk about kind of, okay, we do this here locally in the SPL somewhere in the basement of a hospital, but how do we get out? And so I'll talk a little bit about that aspect. So again, the overall problem that if you look at what I've been doing for the last 30 years is basically how do you take image data and convert it into relevant information. And I'm giving you here an example where you see here in the example of diffusion tensor imaging, and I'll talk more about the topic later in my presentation. What you see here is a representation where the MRI-derived diffusion tensors in each voxel are represented as a small colorized ellipsoid. And what you really see here is that there's so much data that you don't see anything. And so what we need to do is analyze the data, extract meaningful features, and here you see a rendering that was generated from data that started like this, where you have some 5 white matter tracts, and you have here these white structures which are creases that separate those tracts. All of these are mathematical constructs and fairly fancy mathematics actually. But then finally we take those white matter tracts and now map them into a patient's data set. So this is a patient with a brain tumor in this area. The image that you see here is actually obtained from an MRI scanner that is inside an operating room, so an intraoperative MRI scanner. And so you see here the white structure surrounding the brain is actually the subcutaneous fatty tissue. And you see it's interrupted here because the craniotomy has been performed and there is a skin flap. And so this is an intraoperative image. We have taken the preoperative images, MRI, fMRI, DTI, and mapped it into the intraoperative configuration. And that's the overlay that you see here. So from data all the way to something that potentially is clinically useful. And in order to do this, we are actually active on different levels of science. So we do algorithm research, we do software tool development in order to take those algorithms and turn them into tools that can be used. And finally, we take those tools and use them to do biomedical applications. And again, you need to have an end-to-end solution if you want to have an impact in this field. So it's not enough to do algorithms. It's not enough to generate applications. You have to have everything together. And here again, example. So this is an algorithm, brain mapping, conformal mapping of a brain to a sphere. Then here you have a tool. This is a tool to do analysis of CT images of the lung, actually bronchial wall thickness to be more precise. And here again, an application, neurosurgery, where we take all of the results of this analysis and put them together into a single comprehensive display. And let me repeat again, I'm giving you examples. I could have had many more examples. So these are just examples of applications, examples of algorithms. So again, what it requires is to work in interdisciplinary teams. And interdisciplinary teams, it's always difficult to build them. It's always a challenge because everybody needs cross-training in the other specialty, and that takes time. Miscommunications are a given, so everybody has to be flexible and willing to basically assume that there was no bad will. But still, it is not an easy thing, and many people don't succeed in doing this, but it is very important for this style of research. So that's enough philosophy. So now let's get a little bit more practical. So first I'll talk a little bit about the SPL, and then we'll get into the science. So the SPL is a local resource, so it's a lab inside the hospital in the radiology department, which puts us into a good position to collaborate with different other departments, because that's the inherent role that radiology has in a hospital, is to provide services for other specialties. And that put us in a good position to do the same thing. We are specializing in interdisciplinary research, and of course we have a network of strong collaborations, both local, but also in the hospital, in the city, but national and international as well. And there are several layers to this cake. So we have the scientists that do research, and again, the research spans all the way from applied mathematics down to surgery and everything in between. So different styles of research. So I've taken on the habit to ask, so what's your research? What's your science before I get into a discussion? Because one person's science is the other person's application. So that's again another type of pitfall that we can fall into if we are not careful in interdisciplinary work. You need an engineering group that takes those tools and makes them usable. And that's sometimes an enormous amount of work. You write the algorithm paper with a little MATLAB script, and then it takes you 5 years to get it into a tool that the biomedical scientist can use. And finally, you have an environment, an IT environment, so you need an operation group, a sysadmin group that will basically maintain and keep that environment stable. Now, there are inherent conflicts between those groups because the engineers want to try new things, and the sysadmins want to freeze everything, characterize it, and keep it exactly the way it is. And so it's a constant balancing act between those two contradictory sets of requirements. And at the SPL, we have a IT environment that is really designed for science, as opposed to one that is designed for HR operations or administrative purposes. And it is also oversized compared to the size of the group, because we want to have basically easy access for people in our environment. So we oversize everything. And over the years, we have local services, but increasingly we also have global services where many of our capabilities are virtualized and accessible kind of from remote locations in a more or less transparent way. And local control means we are not part of the hospital's IT environment, but we are separate from the hospital's IT environment. And I've had a lot of entertainment maintaining that independence. But I think that we've had several instances where the hospital's IT people tried to take us over. And but at the end, I prevailed, and I think it's very critical because our priorities are very different from the hospital IT's priority, which is more an operational group as opposed to a research-oriented group. And of course, it's not just hot air and talk, but at the end you have to have computer room with some big iron, our cluster computer. We have a variety of different machines in the rooms. We have also offices and facilities and shared facilities for the users to have local access in addition to the remote access. Okay, so that's kind of the anchor where we are based, and we have several physical facilities inside the hospital environment. Now let's talk a little bit about the science, and I selected two topics to talk a little bit about some of the science and to show you what we are doing and how we are going about it. The first one is the EM segmenter. So EM stands for expectation maximization, and that's a statistical mechanism. And Sandy Wells basically started working on that project about in 1992, when one of my collaborators, Martha Shenton, came to him and told him, you know, we are doing this threshold-based segmentation, and there is kind of this funny effect that the gray matter doesn't look the same everywhere. And so Sandy looked into it, started looking into the MR physics side of it, and what came up with is the following. So this is one slice of a volumetric acquisition of the brain. It's a coronal slice. Coronal is an orientation like this, like my hand, as opposed to axial and sagittal. It's a coronal slice through the brain. So quick primer. So these are the frontal lobes, and these are the temporal lobes of the brain. The brightness here is the white matter, and this here is the gray matter. Now these are MR images, so the fact that it's white and gray is more or less a chance thing. I could have shown you T2 weighted images and the contrast would be reversed. But another thing that you see, if you look at the signal intensity of the white matter here and compare it to the white matter here, you see there is a difference. The white matter down here is a little bit darker. And the reason is that basically when you do MR imaging, you're doing an RF measurement, and you wrap the patient's head with a RF coil. And that RF coil has a gain field. And the gain field is not completely homogeneous. The MR physicists are trying to build RF coils that are fairly homogeneous, but they are not entirely homogeneous. And so basically that inhomogeneity of the RF reception characteristics of the coil resulted in the signal intensity fluctuations. So the EM segmenter essentially tries to estimate the classification of gray matter and white matter, uses that to estimate the gain field, then reclassifies into gray-white matter, re-estimates the gain field and iterates until it gets to a point of convergence. Now, if you just use a threshold criterion on this data set, as I mentioned, this is just one slice, but it was really a volume covering the entire brain. So if you use thresholding, then you lose, obviously, the temporal lobes because they are as dark. The white matter in the temporal lobes is as dark as the gray matter up here. And so 3D reconstruction from this type of classification will end up looking like this. So this is a 3D model of the white matter of the brain based on this segmentation. You use the EM segmenter. It can correct for these gain field fluctuations, and accordingly you pick up the temporal lobe that you didn't pick up here. Okay, so that's step one. This is 1993. Now, often our MR images are noisy because when you have an MR scanner and the RF measurement and everything, you have a signal to noise per time cake. And you can slice it any way you want. You want more signal to noise, you spend more time. Or you can keep time and signal to noise the same but lose resolution, which affects the signal per voxel. So you can play different games, but typically because time spent in the scanner is very precious, we are trying to have as short duration as acceptable. So we end up with noisy images. That's what I'm trying to say in a long-winded way. So in between 93 and 98, we worked on how to get some noise robustness into the algorithm. So you run the EM segmenter on a noisy image, you get a lot of misclassified voxels. So individual voxels that, because of the noise characteristics, look like a different tissue class. So you can take basically neighborhood information into account when you do the classification. So the simplest thing to do is you take like a 3x3 neighborhood around the voxel, and then you figure out the median, and you use that as a way to do it. It's a median filter-based approach. Can be used, but there are more sophisticated methods that will produce better results in these areas where a simple median filter might blur out details that are important. Requires more computational power. So Tina Kapoor worked on this at that time on a IBM PVS system, which at the time was a high-performance computer many, many years ago. Basically getting to a point where we were able to take this image and instead of producing this result, producing this result. Now, when I go back for a moment, so I told you this is the white matter of the brain, this is the gray matter of the brain. This image, by the way, is a sagittal image, and you see here the eyeball. The eyeball has been classified as gray matter, but it's clearly not gray matter, it's the eyeball. I just told you so. So how can I tell the computer? That actually turned out to be fairly challenging. And by the way, when I'm giving you this story, do understand we are not isolated. It's not like we did everything and nobody else did anything. We are embedded in a fairly large international research community. I'm talking about my work, but there is corresponding work by other groups. So I don't want to create the impression that I think that we did everything and nobody else did anything. But we did build an atlas. And after several years of work, we got to a point where we could take this atlas and map it into a subject data set. And the first report out of our group using our particular approach was in 1997. But until we got to a point where we could do what you see here, took almost 10 years. I mean, 2004 is not quite 10 years, but took a long time to get it further. Now, this just takes anatomical regional information. And what you see here are altogether about 30 plus structures that have been automatically labeled using in a subject data set using the atlas information. Now, what you want to do, of course, is to have also a model of the variability of each of those structures. So if you look around the room and you compare the shapes of the noses of your neighbors, you'll see everybody has a nose, and I don't see any pathological nose in this room, but you'll see a lot of variability. And the question on how we capture variability in a way that we can take this into consideration when we are working on these algorithms is again a question that is a challenging one, and there has been a lot of work in the field for more than a decade on that particular topic. But we have added in this train where we started with the simple algorithm, the noise reduction, then parcellation, regional information, and now we have added another component to it, which is a model of variability for each of those structures. So what you see here is the superior temporal gyrus here, gray matter, white matter. And this is now a variability model for the gray matter of the superior temporal gyrus based on 30 manually labeled data sets. So somebody sat down, slice by slice, labeled the gray matter in the superior temporal lobe for 30 subjects. And all this information was used to generate this shape model that we now can use to make the algorithm even more robust. And so now, 2007, we are at the point where we have a better version of this entire technology with all those components sitting inside the newest version of Slicer. And these are first results that were generated with this particular tool. And the tool has a workflow built into it where it guides you step by step through the steps that are necessary to set it up before it runs. And of course, we have this statistical engine, we have an anatomical atlas, we have the shape models. These are all modular components. So you swap out the brain, you throw in a hand, you swap up signal intensity from MR, you throw in signal intensity for CT. And that's what Vince Magnotta and colleagues did out of Iowa using our EM segmenter. And they basically used it to do segmentation of hand bones as part of a biomechanical modeling project that they have. This, by the way, is one of the few pictures that are not yet paper. This is not yet published. Okay, so this was EM. So EM, expectation maximization. So now let's go to DTI. And by the way, we live at the interface between computer science and medicine, and both specialties love acronyms. So we have acronyms galore. Everything is an acronym. We have even cases where you have acronyms of acronyms. So diffusion tensor imaging. So what you are doing in diffusion tensor imaging, you are doing an MR acquisition. The MR acquisition, simply said, basically you're looking at the velocity, things moving. And then you scale the acquisition to be sensitive to things moving at the scale of Brownian motion, at those speed ranges. And if you do everything right, you can basically look at the motion of water. And that basically, if you think about water, if you have water in a cup, in the center of the cup, the water molecule can move in any direction. And that gives you Brownian motion, so if you add up the motions of many, many water molecules, you'll get essentially a spherical distribution. Now, if you take a lot of straws, like drinking straws, and you put water in, and the straws were very, very tiny, not big ones, but very, very tiny. The water molecule motion is unrestricted along the axis of the straw, but in both other directions, it will be very restricted. So in that scenario, you'll get actually, if you do the same measurement, instead of a sphere, you'll get a cigar. And so people basically measure the motion, and you can do a measurement you project only in one direction. So you do multiple projections and put them together, you'll get the tensor of the diffusion tensor. And so if you do this analysis, what you see here, these are areas where you have primarily linear motion, and here you have primarily spherical motion. Now, the spherical motion in this particular slice, which is a coronal slice through the frontal lobe, corresponds in this example roughly with the gray matter of the brain, where you have usually the organization of the neurons is such that there are multiple connections in many directions. While here you see linear organization, and that corresponds actually to areas in the white matter of the brain, where in some areas the fibers are highly organized and really parallel. That's the basic idea. So you measure a diffusion tensor, and then you have this tensor, and now you want to do analysis and turn it into medically meaningful information, and it turns out to be a challenge. So the first thing people did is basically just come up with fancy displays on how to show the tensors, and this is one example. What we have here is basically, remember I told you a sphere and the cigar? So if it's a really elongated cigar, you get a very long blue line, and when it's almost a sphere, it's closer to a dot. And in this particular display, if the main direction is in slice, you just have this blue line. But if the main direction orientation of those tensors is out of slice, they added a colored dot. And so here you see, for instance, this is the corpus callosum, which connects the right and the left side of the brain. And you have a lot of parallel nerve fibers in that area, and they go from left to right, and so they are in slice. And so you see here mostly blue. Here you have another one, the cingulum bundle, which is perpendicular to this slice, so it goes from the front to the back, or vice versa. And so you see mostly orientation out of slice with this red color. So now we've labeled every voxel with something. Now the next thing is, okay, I told you corpus callosum connects right side to the left side. So I would like to take all of these little lines, the little blue lines, and connect them together. And so here you have a corpus callosum. You remember up here and down here, this is corpus callosum. Here you have a brain tumor. So here we can follow, basically jump from one voxel to the next one, and we get these nice lines together. But the tumor has changed the organization of the white matter in this area, and so the tracts stop here. So this is an invasive tumor, and so that's one way to use tractography to help in understanding what's going on in the white matter of the brain. People got very excited about diffusion tensor imaging because until the technology became available, there was no way to look what's going on in the white matter. The white matter was just a homogeneous blob of white matter. There was no functional information that could be extracted, like functional MRI can be used to extract information about brain function, about the cortical gray matter function. But there was no equivalent until DTI came along. There was no equivalent for the white matter. So there has been a lot of excitement about DTI because of this. So now, you remember I told you corpus callosum, there are a number of other tracts that anatomists have named. And so we are now able to create those little lines. So can we group those lines into kind of meta groups and see if those correspond to something that the anatomists have named? And so what you see here is first work around 2000 in our group. This is the corticospinal tract, left and right, and these are components of the corpus callosum. Next step, you do this tractography instead of seeding it for a particular targeted tract that has a name. You say, let's throw all the data into statistical analysis, and let's use some form of proximity. So we have extracted those fiber tracts, I call them spaghettis, and now some of them are running parallel to each other, and they should be grouped together. And others are not running parallel, but kind of perpendicular, so they shouldn't be grouped together. So people started working on doing this kind of analysis where the tracts, we extracted the tracts, then different features were analyzed, and then a cluster analysis in feature space was performed to basically assign these colors that you see here. Now, you remember the corpus callosum that I mentioned before that connects right and left half of the brain? So here you see parts of the corpus callosum in blue. This is a view from above. Now you see this green structure here, that is the cingulum bundle. So even though this is an unsupervised statistical clustering approach, it has resulted in classifying some of the structures that anatomists would have named as well. So it's promising direction. And of course, some continued work. We had one collaborator, David Banks, who worked on some of the visualization. So he took the results of these clustering algorithms and basically looked at how to render them with shadows and more advanced lighting models. If you look at the lighting model here, it's a fairly plain vanilla one. And that's essentially the same data, but with a more sophisticated visualization approach. Okay, so I showed you a lot of pretty pictures. Now, of course, I showed you these spaghettis, and what we show are basically spaghettis about 1 to 2 millimeters in diameter. But we are saying those are corresponding to white matter tracts. And those white matter tracts consist of individual neuron axons, which are in the order of magnitude of a few micrometers in diameter, so even less. So what's the correspondence between our mathematical construct that is essentially based on statistical sampling and those, I mean, what you see here in the actual white matter tract? So how do we validate this? So, and I'm showing, this is the only example that I'm showing you about validation. So validation is a very difficult thing in our field. We have images, it's usually not very practical to get gold standards. And if you don't have a gold standard, then you compare two methods, but you still don't know which of them produces the true result. So ground truth is a very finicky and elusive goal in our field, and it plagues the field for a long, has been plaguing it for a long time. So Carl Friedrich Westin basically decided to take a stab at it for DTI, and so he actually did experiments in macaque monkeys. So what they did is pressure injection of a substance that follows along the axons. Then they sacrificed the animals and did histologic analysis and compared it to the MRI in the same brain. So what you see here is the microtome that actually is cutting the embedded brain. So you see here the brain embedded in a support matrix. Here is one of those slices, and here are the slices being prepared. So it's a lot of very detailed and gruesome work. And so these are the results. So what you see here is the results of from the histological section. So the injection of HRP was done in the motor cortex. And here you see some of the fibers that were stained through the HRP diffusing along the axons. And so this result now put together, what you see here are several tracts manually outlined slice by slice from the histologic sections. And here you see the same tracts extracted using DTI post-processing on the same brain based on MR images. And if you look at this, you see that the correspondence is striking. And so this was published very recently in Neuroimage. Okay, so those were two examples of some of the scientific activities where I just tried to show you a little bit more in depth. Now, of course, I haven't shown you any formulas, and that's on purpose because I couldn't explain them, so I decided not to show them. I can explain the images. So now let's go a little bit to the engineering. So we talked a little bit about science. Let's talk about engineering. And again, I just choose two examples here. One a little bit about high-performance computing. And in that field, I've been working on HPC applications for many, many years, as Jill knows very well. She helped us get a connection machine into the lab a long time ago. And so I just picked one little example, a relatively recent project there. And then I'll talk about Slicer. So the example that I choose is doing high-performance computing in image-guided therapy. So you remember I told you we have intraoperative MRI available. And so we can take images during the surgery. So what you see here is such an example. You see again, remember subcutaneous fatty tissue, the white line around? And it's broken here. And as a matter of fact, this is an image almost at the end of the surgery. This black hole here is what used to be the brain tumor that the surgeon has rejected. Now, if you compare this preoperative image with the early postoperative image, you see that here locally you have significant amount of changes. So if you would like to take the preoperative images and use them during surgery, you have to non-rigidly warp them to map them into the brain in the intraoperative configuration. And this is pretty challenging, and people have worked on this topic for quite a while. One of the lines of research we did along those lines is to use a finite element method. So take the images, generate finite element meshes, and then do a finite element biomechanical simulation of the deformation between time point 1 and time point 2. Now, that's nice and well, but the first one that we did took about 20 hours to compute. And that was on a high-performance computing machine. So 20 hours is good enough to write a nice scholarly paper, but it's not good enough if you want to go to the point where it can be used during a procedure. And so we worked parallel tracks. On one hand, we worked on algorithmic improvements, and in particular, mesh generation is one place where you can gain a lot of time if you have good quality meshes, because the fewer elements you have, the faster the computation. And of course, if you don't have enough mesh elements in the right place, then your accuracy is not good enough. So it's a trade-off there. And then the other part is, if you need faster, you just get a bigger computer. Now, that's very easy to say, but getting the computer is only step one. Then you need to take the algorithm and make it work on your bigger computer. That turns out to be challenging. Many, many years. I mean, this is now almost 10 years of work. That what you see here is basically the pinnacle. So the latest iteration, we are now working with Nikos Chrysokoides from William and Mary, and they have a big compute cluster machine there, and they are interested in how to do this type of high-performance computing, grid computing through the web. And so the application that we have evolved, so you have here the two images, the data gets transferred to the cluster, the analysis gets run, they do the mapping, deformation field. You see here basically the vectors that show you kind of the deformation, applied to the data, and that then allows us to take preoperative images like DTI and fMRI, which sometimes might take hours to acquire, and map them into the intraoperative data set. And they are right now working on an interface to that entire infrastructure into 3D Slicer, which will allow basically a technician in the operating room to do it. Now, this is not yet at the stage where we are ready to sell a product that's FDA approved, but it is at the stage where we are getting close to do clinical research with it. And so I raised now this word, so let's talk a little bit about 3D Slicer. Those of you who know me know that I'm one of the salespeople for 3D Slicer. And 3D Slicer is a visualization package initially developed for IGT. And one of the first versions for 3D Slicer, or one of the prototypes, was actually done by Nobi Hatta, who is here in the room. It's now over 10 years old, and in the meantime, we have just started about 2.5 years ago to develop a new generation of 3D Slicer that was re-architected from ground up. And as you can see, at least 80% of the code was rewritten. So we didn't just put a pretty face on the same old skeleton, but this has really been rewritten and re-architected from ground up using all the experience of 10 years of heavy use. And it can do a lot of things. It does visualization, it does different image processing things, filtering, registration, segmentation, DTI. It has IGT capabilities, and it has a plug-in architecture to interoperate with external programs. And this HPC example that I gave you is basically leveraging this plug-in architecture, which uses XML wrappers. And we are also beginning to interface Slicer to informatics frameworks, and there's work with Randy Buckner's group. You remember that he talked about XNet a few months ago in this forum, and basically that's one of the informatics frameworks that we are interfacing to. Another effort that is going on right now is to interface it into ontological and query frameworks. So where you have an image, and here you have again an atlas, and this time it's the MGH brain atlas mapped onto a subject. And basically each of the colors here represents a different anatomical structure. And what you see here, these blobs, these yellow blobs, these are actually fMRI-derived activations from that subject. So you have a generic atlas mapped into a subject. On the same subject, fMRI analysis was done, and all of this information is available in the same coordinate system. And so you can now basically point at the place, and you get here the name of the structure. And so you see, now you can just point at it and say, we see an activation in the superior temporal gyrus. And so the ontologic framework allows you now to translate this and use it as a start point for searches into Google or other search engines. And as I mentioned, I'm not going to talk a lot about XNet because Randy talked already a lot about it. But it's a framework where what we are working on right now is interoperability, where you have here an XNet-based database, and you basically can select a study and download it into Slicer, do analysis and whatsoever, and we expect that within a short time you will then be able to take the results of your analysis and upload them back into the database, so interoperation in both directions. Now, and of course I talked about medical. I decided to focus my presentation on medical, but we have of course non-medical applications, and the collaboration with Alyssa, where we are using the slicer to do analysis of completely different data sets. This has nothing to do with medical, but to say it a little bit flippantly, images are images, and as long as you have 3D raster images, we can do something with them. And so this is one example of some of the work that is going here with IIC. We have another collaboration, and again, just as an example, where we are looking at confocal microscopy data. And this is the confocal microscopy and astrocyte, and that's a collaboration with Nick Mir over in San Diego. They are interested in synapses in astrocyte and how they are distributed. So just two other examples. I could give you a few other examples. Somebody, and that was, we didn't even know about it until I sent out an email asking for examples of use. Somebody used it to do visualization for simulated soil erosion. So they were simulating soil erosions, and if you look, this is 70 kilometers by 10 meters. And they are modeling how particles are being transported down a grade. They used slicer to do the visualization. Okay, so last few minutes, I'll get onto my soapbox and start agitating. And so where this started is kind of, okay, so we are doing our good research, or we think it's good research. We collaborate like good scientists with other scientists. But then how do you make all of this accessible, and how do you interact with other groups that are your peers, as opposed to, quote unquote, your customers or your collaborators? And how do you share tools? And I got frustrated so often when I saw something and they gave a nice presentation, and then I go and ask, can I have it? And they say, yeah, in principle, yes, but you know, we have this agreement with this company, and so you have to sign this, and we might be able to give you that, but we are not sure. And so over years and years of this, basically moved more and more into the field of free open source software. Now, I'm not saying that force is the answer to all of our questions, but in science, I think free open source software is something that will be of increasing importance. It's already now has a lot of visibility in the field, but I think that the importance will increase, in my opinion. So a few years ago, about 4 years ago, NIH came out with a RFA for National Centers of Biomedical Computing, and we put together a team, basically, and submitted an application that was successful. So from my point of view, that was expanding beyond the SPL. How do we interoperate with other groups that we would consider our peers? That was really the driver behind this. And so NAMIC today, a lot of people, so each of these dots represents one of the NAMIC participants. And as you see quite a number of people. So it's a very complicated grant, and Mark Ellisman, who has a different multi-center grant, always says it's like herding cats, trying to get scientists to work together. And it's big science. And big science done right can be a force multiplier, because if you can get my file reader, you don't have to write your file reader. You can just use mine. The time that you would have spent otherwise to write your own file reader, you can use to do research. So that's kind of a simplified version what it is. It also, in particular, if you combine it with open source, encourages openness and quality and trust, because if I can look at your code, you better don't hide something, otherwise I'll see it. With commercial or closed code, whether it's commercial or not, sometimes you really don't know what you're getting. You're getting a neat black box. You don't know what's inside. But it requires a change in culture, because traditionally science is really done in most areas of science in small groups. And so it requires people to change the mental vantage point from my research to our research. It sounds very simple, but that's, at least in my experience, is one of the biggest challenges really in doing this type of research, is how you get people to change their attitude. And at least in the field of software, free open source is an enabling technology towards that goal, if you agree that that's a good goal. And for NAMIC, we have adopted a very liberal approach to open source, where you can take it and you can use it any way you want, including commercial use. The only thing that we ask for some of the packages is an acknowledgement, but there are no restrictions on use. It took me more than a year of negotiation to convince the hospital that that could be done. I mean, first they said just no, and then we started negotiating. So the institutions, and I think we are not alone in that, but institutions are not yet used to that model of operation, and there is some educational activity necessary on the institutional side if you want to change those licenses. But if you do it, as I said before, there is a value proposition there. It's cost effective because you can use other people's work instead of having to reinvent the wheel. It can result in high quality, and the openness and the ability to scrutinize somebody else's code and help debug that code is a very big plus. Because if it's open source and that particular piece is something that you need really in a mission critical way, you can fix it yourself. You don't depend on somebody else's priorities to get it fixed. And that's sometimes in itself a very important thing. And if it's open source, you can just share it with your friends. You don't need to become the sales agent for a company. Now, in some cases, don't misunderstand me, I'm not against companies, but I think in scientific software, where usually the number of copies is relatively small, it sometimes turns out to be a hurdle. Now, we took a number of software pieces. Most of those predate NAMIC, and we put them together into something that we call the NAMIC kit. The NAMIC kit is more a portal where we say, if you take this piece and that piece and the other piece, we know it works together. Here are examples how to make it work together. It's modular. All of this stuff is open source with no strings attached. So if you build whatever you do on that basis, then you can share it like any other open source software. And so it's a little bit like the seal of good housekeeping, that the way you can think of it, as opposed to if it's in the NAMIC kit, we own it. And so there is the 3D slicer. There are toolkits, the Insight toolkit, the visualization toolkit. This is a widget set for interface elements, KW widgets. And there is an entire software engineering methodology that we have adopted with multi-platform support, automated testing with dashboards, and so on. So there's a lot of very computer sciencey material there. Now, I think time is more or less up, so let me close up a little bit. So you remember I started, how do we get from data to information? Now, as it turns out, the more we can analyze the data, the more data gets produced. If you look at all the imaging modalities, what they have in common in the last decade is the explosion of data produced. And it's not just that we get more data, but even the rate of acceleration is increasing. So we get literally inundated with data. So if you ask my personal opinion, I think that the need for this type of post-processing ultimately, as a sophisticated way of data reduction, will actually increase in importance over the next decade or so. It will be more important than it was. Many fields that didn't face this issue 10 years ago are facing it today, and I think this trend will also continue. So, as far as I'm concerned, there is a lot of job safety there for me. And so we'll see more algorithms, more software packages, more end-to-end applications that will coexist, which will make life confusing for the quote-unquote end users of these efforts, the application scientists, because there will be a variety of packages, and we need to deal with it. But I don't think that things will get easier. They'll get more complicated. And I think that we are in a good position to continue working in that direction. And many of the things that we are doing go beyond medical. I focused my presentation on medical so that I could kind of chew with you so some of the concepts, but none of it is limited to medical. I showed you the astronomy example where we use this package in a completely different field. It's a very nice example, but I know it's not the only example. And similarly, it's not some of the things that we are doing in imaging, but for instance, the software methodology that we have adopted is not limited to imaging. If you need multi-platform compiles, you can do it whether it's an imaging packet or not. As a matter of fact, the kitware CMake environment has been adopted by the KDE community, which is one of the two big communities that develops software for the Linux desktops. For the, I think release 4 will be produced with CMake. So they switch from a different tool. So as an example. Okay, and if you want more information, here are some URLs where you can find more information. So that was it. Thank you very much.